Resistors and the resistance. We're going to cover 3 topics. Number 1, Ohm's law and the resistance. Number 2, how resistors combine, including parallel and series. Number 3, electric power. Electrons move randomly in a conductor, such as a metal. So here Al represent aluminum metal. So when the electrons becomes a free electrons, and they move around all different nuclei of aluminum as if they don't belong to a particular atom. Then these electrons can form a current. They can flow along some directions when a voltage is applied. So when you apply a positive voltage on the right and negative on the left, the current will move from positive to negative. The direction of current, by definition, always moves from a higher potential and to a lower potential. So let's look at the current. Current is one of the 7 most basic physical properties. And current is the amount of charge passing through a cross-section per second. So it's the charge divided by time. So 1 ampere equals to 1 coulomb per second. So here is current. Ohm's law. If we have a resistor and we apply voltage on it, it turns out the current that flows through the resistor is proportional to the voltage applied. And this is what we call Ohm's law. So the resistance is created when these electrons are moving. As a matter of fact, the positive charges, the aluminum ion, they do not move. The electrons move. So when the electrons move, they can hit on other aluminum ions or can hit on other electrons. That creates resistance. So resistance, as a result, is a device constant. Resistance is the voltage over the current for a particular device. So this is the device constant. The SI base unit is ohm. 1 ohm equals to 1 volt per ampere. Well, let's look at electric wires because we use them very often in all kinds of circuits. Electric wire, if we consider them as in cylindrical shape, then let's take a very short piece. So this piece, the length is L and the cross-section area is A. The resistance equals to the resistivity rho multiplied by the length and divided by area A. So the resistance is determined by the shape of the wire. And the longer the wire, the more resistance. So whenever possible, we can use shorter pieces of wire to reduce resistance. The resistivity is a constant a lot of times if at a certain temperature. When temperature changes, the motion, internal motion will increase and the resistivity will change. So therefore, the resistivity value we have is always for a particular temperature. So for example, there's a room temperature resistivity. That's when the wire's resistance is defined. So you can see when temperature increases or decreases, the wire's resistance can change. When design a circuit indoors, then the temperature is probably somewhere close to the room temperature. But if you design any device or circuits that's used outdoors, then you have to take into consideration the fact that the wire's resistance can actually change with temperature. So here, let's have an example. Interesting fact is that 90% of power consumed by any light bulb. So in this case, we say it's a 110 volt, 40 watt incandescent light bulb. Emitted is heat and only 10% is light. That's why this kind of light bulb is not as energy efficient as a fluorescent or the LED light bulbs. So for example, let's see, if we have voltage equals to 110 volts and the power equals to 40 watts, what is R? If we dig into our toolbox, actually we are going to introduce this. The power equals to current square times R, or voltage square divided by R. By the way, we will introduce this. Apply this will give you a resistance. So for the light bulb, although we label it 110 volts and 40 watts, the constant is now 40 watts. 40 watt is the power only when you plug it into 110 volts. What is the constant is the resistance R, 302.5 ohms in this case. Next, we talk about resistors in combination. When we connect resistors in series, then the total resistance is the sum of individual ones. When we connect the resistors in parallel, then the 1 over the total resistance is the sum of 1 over R1 plus 1 over R2 and 1 over R3. Okay, so one example, series connection, 1 ohm plus 1 ohm is 2 ohms. So that creates higher resistance. Example for parallel, 1 ohm plus 2 ohms is 0.67 ohms. So when you have two resistors in parallel, the resistance actually decreases because there is another pathway for electron to flow through. Extra example, 1 ohm and 1 ohm in parallel creates a 0.5 ohm total resistance. That may be a little counterintuitive. So let's look at this here. It's a combination of resistors and capacitors. Last topic we introduced, number 3, is electric power. For any device, electric power is defined as the current multiplied by the voltage. So it's 1 volt times 1 ampere equals to 1 watt, W-A-T-T, or 1 joules per second. For resistors in particular, the power is also called heat dissipation because this power is converting electricity to heat most of the time. In the case of light bulbs, sometimes it also glows and give out light. But for majority of the resistors, including heaters and just wires in general, the heat dissipation rate is the amount of electric energy that's converted to heat energy per unit time. So example, let's look at a light bulb again. If a 110 volt, 40 watt incandescent light bulb is plugged into a 220 volt power supply, what is this power? Is it still going to work as designed? So given voltage, power, new voltage, what is the new power? R is a device constant, so P equals to I squared over R equals to V squared divided by R. So from here, we find the device constant, which is R 302.5. Using that, then plug in the new voltage, then the power becomes 160 watts. So you can see the wattage, or say the power of a light bulb, it's not its device constant. The device constant for a light bulb is resistance. In summary, we introduced 3 topics: Ohm's law and the resistance, resistor combination, and electric power.